I'm going to write out the form of two equations here, and I want you to tell me which process each of these equations is. We're going to have something, we'll call it element A, that's going to element B plus C. Doesn't matter what element A is, it doesn't matter what B and C are, but element A is changing into B and C. What kind of process is this? This would be nuclear fission because we've got one heavy thing that's splitting apart into two lighter nuclei. Now, what else do we need here in nuclear fission? We don't use the other things in determining whether it's fission or fusion, but we need it in terms of making fission happen. Tell me something that we need on the left-hand side besides element A. We need a neutron. Right? We need a neutron to kind of kickstart this to take place. What else do we need on the right-hand side? We need more neutrons. It might be 2 neutrons. It might be 3 neutrons. It depends upon the particular nuclear fission reaction, how many neutrons we're going to get on the right-hand side. But there are going to be more than one neutron on the right-hand side. What else do we end up getting on the right-hand side as well? Energy. And of course, what reaction it is determines what kind of energy or how much energy we get out of it. Of course, the fusion reaction is going to look something like this, right? We've got A plus B forms something that is bigger, so we'll make C bigger. What do we have to have on the right-hand side? In addition to element C, whatever that element is. Helium-3 in the example that I gave you in class, but it could be any one of a number of things. What else we got on the right-hand side? Somebody said it. I heard somebody whisper a neutron here. Okay, you got a neutron that's produced there. What else we got on the right-hand side? You got to have energy released here, right? And of course, in this one, you also need energy to kind of kickstart this into happening. But the energy that comes out of it is going to be way more than the energy that comes into it. Otherwise, it's not going to be exothermic. And of course, then it wouldn't be a fusion reaction if it wasn't exothermic. So far, so good? All right. There is energy that comes out of it in both cases on the right-hand side. Where does that energy come from? What do we call that energy, by the way? What's the term that we give to that energy that comes out of the nuclear reaction? I'll give you a hint. It's a 2-word term, something energy. Binding energy. Good. It's the binding energy. And we define binding energy in a number of ways, but the way that's relevant for us is the energy that comes out of this nuclear reaction, the energy that's released by this nuclear reaction. Where does it come from? In either case, the fission reaction or the fusion reaction, where does the energy come from? Can't get energy from nothing, right? Got to come from something. Tell me what it comes from. It comes from the mass defect. How do we define the mass defect? There was 2 ways, remember, right? One way to define mass defect. If you got one of the 2 ways, that's good. Just tell me what it is. You don't need to give me both, Jordan. Good. The difference in mass between the nucleus and the nucleons. Okay, the nucleus has a different mass than the nucleons, the protons and neutrons that make up the nucleus. Can you tell me which weighs more, the nucleus or the nucleons combined? Yep, the nucleons. If you add up all the mass of the nucleons, it's going to give you a certain value. If we compare that to the mass of the nucleus that's made up of the nucleons, well, then the nucleons together have more mass than the mass of the nucleus itself. What's the other way that we define mass defect? Good. The difference in mass between the right side and the left side, or the products and the reactants, or the daughter nuclei and the parent nuclei. Good. Difference in mass between one side and the other side. Which side is going to be heavier? The left side or the right side? The reactants or the products? Do we gain mass or do we lose mass in this reaction? We're going to lose mass, right? The difference in mass, the mass that's lost, the missing mass, sometimes we call it, is called the mass defect. Now, what do we do with that mass defect in order to turn it into this energy that ends up being released? How do we find the value of that energy? This one's easy, right? You got mass defect, you want to find energy from mass? We're going to use that equation, E is equal to mc squared. We also defined a term called U, the atomic mass unit. Those of you who have taken chemistry will be familiar with this one. One atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. We want to do the conversion. We'll set 1 over 1.66 equals x over whatever. Yesterday you had 3 problems to do for homework, which involved mass defect and binding energy. Okay, we needed to find in those 3 problems the mass of the left-hand side, the mass of the right-hand side, subtract them, then convert that mass defect in atomic mass units to kilograms, and then use the equation E equals mc squared in order to find the energy that's released, or the binding energy here. Those questions that we had last night were on page 819. Any issues with any of those 3 questions on page 819, please? Yep. The question is it always going to be products minus reactants, or can it sometimes be reactants minus products? You want to get a positive value, so we're going to say it's reactants minus products, just to get a positive value. But strictly speaking, the mass defect would be a negative value, right? We'd lose mass. So strictly speaking, it's actually products minus reactants. Bottom line is you're going to get the same magnitude either way. What you do when you get that value, whether it's reactants minus products or products minus reactants, doesn't really matter. You're going to get the same magnitude. One will be a negative value, one will be a positive value. Just make it positive. So it doesn't matter which way you go, just make it positive. All right, let's take a look at question number 2 and 3. Okay, 3 is pretty similar to question number 1. Once we have the balanced equation, question 2 requires us to get that balanced equation, as opposed to question number 1 where it's already balanced here. So question 2 says, we got uranium-235 absorbing a neutron. And that part's fairly straightforward. Uranium-235 absorbing a neutron. It splits into bromine-87 and lanthanum-146 plus a certain number of neutrons. We've got to determine how many neutrons we have that are produced here. Okay? Probably the easiest way to do that is pretend we don't have any right now. Let's just pretend we don't have any. On the left-hand side, we've got 1 plus 235 is 236. 0 plus 92 is 92. On the right-hand side, we've got 87 plus 146. That's going to give me 233. 35 plus 57 is 92. So we're missing 3 from our mass number on the right-hand side. How are we going to get it? Well, we can't introduce 3 protons because that's going to change 92 to 95. The only way to do that is to introduce 3 neutrons. Now we've got 233 plus 3 neutrons, giving me a total of 236. So it's going to look something like this. This is my balanced equation. How many people got that? Okay, good. Now we want to find the energy that's released here. To do that, we've got to find the energy of each side. We're not going to go through the entire mathematics of this because there's lots of numbers, like 6 decimal points for each of them, and it takes a little bit of time to go back to that table and check. But we'll go through the process of it, okay? Let's get the mass of a neutron. I think it was 1.00 something, something, something atomic mass units. Okay, get that mass. Okay, get the mass of the uranium-235, which you can also find on your data sheet. Okay, when we do that, we get a total mass here. The mass of the reactants. Add them up, right? Get a total mass. Do the same thing on the right-hand side. We're still in atomic mass units. Get the mass of bromine-87 from the table. Get the mass of lanthanum-146 from the table. The mass of 3 neutrons from the table. Add those masses up. Get a total mass. Now again, we're still going to be in atomic mass units. I would bet, if you get a question like this on an exam, I would bet that the masses would probably be given to you in kilograms as opposed to atomic mass units. The reason I say that is because this is a fairly long question as it is. Right? To have to do those conversions just makes it one more step. And as a multiple choice question, that makes it, I think, in my opinion, at least a little bit too long. So I would bet if you see something like this, the mass would be in kilograms, and you wouldn't have to do the conversion from atomic mass units to kilograms. But let's be prepared to do that just in case. Okay? Whether we're in kilograms or we're in atomic mass units, we're going to find the mass defect next. Okay, the mass defect is the mass of the reactants minus the mass of the products. Or you can go the other way around, Courtney, as we said when you asked that question. You're just going to get a negative value. When you go to figure out what the energy is, just drop the negative and make it positive, that's all. That's our mass defect. Now, from that mass defect, we're going to say E is equal to mc squared. All we're going to do is plug the mass defect into there, multiply it by the speed of light squared, and we're going to get the energy that's released, although understand that that energy is going to be in joules. We may have to convert it to electron volts, okay, depending upon what our four options are. Now, we may also have to convert the mass defect into kilograms from atomic mass units, as we do in this case. To do that, remember, we're going to say 1 atomic mass unit, or 1.66 times 10 to the minus 27 kilograms, equals X atomic mass units, equals whatever my mass defect was in atomic mass units over X. Take that value for mass defect in kilograms, plug it in there, and then we should get our answer in joules. Does that process make sense? Drew? Question? The value of the atomic mass of the neutron is in the top right-hand corner of that table that some of you got a copy of yesterday, and some of you just would have had to look in your book. And I believe in the top right-hand corner it gives you the atomic mass of the proton, neutron, and electron. Yeah. So if that's your only issue, Drew, we're not going to panic about that, because in the end, if you know how to do it, the data will be there. The data will be there. And you know what? On the diploma exam, you're not going to get that same table anyways. It's just going to be formatted differently. So it doesn't really matter where it is on that table, as long as you know that you need it and you need to look for it. Okay? It'll be there. You don't need to memorize that number. Good? All right. I would like you to take a look at, please, a multiple choice question. Question number 166. All right, let's take a look at this question now. It says, in 1939, 4 German scientists made an important discovery that ushered in the atomic age. They found that a uranium nucleus, after absorbing a neutron, splits into 2 fragments, and that each have a smaller mass than the original nucleus. This process is known as nuclear fission. They didn't need to tell us that, right? Really, this whole first paragraph, we already know this, right? At least the important parts of it. Those people's names, Hahn, Meitner, Strassmann, and Frisch, or however you say that. I mean, in the end, is that going to be relevant to this question? Not at all, right? Okay, if you know what nuclear fission is, you didn't even need to know any of that first paragraph. Now, it goes on to say there are many possible fission reactions that can occur, 2 of which are shown below. We got a neutron combining with uranium-235, forming uranium-236 momentarily. Remember we said that you briefly get that uranium-236, which in turn splits up. First one, we've got it splitting up into barium and krypton, and the second one, we have it splitting up into xenon and strontium, plus some neutrons. The question 166 asks us for the value of X. It asks us for the coefficient right here. Okay, if we're determining that, we don't need to look at reaction number 1 whatsoever. We need to look at reaction number 2. In reaction number 2, we're going to say that we have, on the left-hand side, forget about numbers here in terms of atomic masses and stuff. That's irrelevant right now. On the left-hand side, we have 236 protons and neutrons, a mass number of 236. We have an atomic number of 0 plus 92, giving me 92. Now, let's forget about this one. It's just basically, we'll just look at this one as a double check to make sure that we calculated this one right? 236, 92, sure enough. Let's look at the final product here now. Okay, forget about the neutrons. Forget about those neutrons for a second. Pretend they're not there. 140 plus 92 gives me 232. 54 plus 38 gives me 92. So what are we short here? We're short some neutrons, right? We're not short any protons because we've got 92 protons on one side, 92 protons on the other side. How many neutrons are we short here on the right-hand side? 4 of them. So we're going to say 4, 1, 0 neutrons. Now, 20% of you said C. 20% of you said 2. I'm just curious where that one came from. Why people said 2 on that. Anybody want to volunteer that? 15% of you said 1. Were they kind of guesses? Were they? All right. Thanks for your input. Thanks for your help on that one. Does everybody understand why it's going to be A there? Okay, I'd like you to do 2 more questions, please. These ones are numerical response, number 167 and 168. All right, let's take a look at these 2 questions now, 166 and 167. We're told that the measurements given below indicate that the mass of uranium-235 has a smaller mass than the mass of the corresponding number of free protons and neutrons. We would expect that, right? We would expect that. We define mass defect in 2 ways. One of the ways, that first way, is the difference in mass between the products and the reactants. Or sorry, that was the second way. The first way we defined it was the difference in mass between the nucleus and the nucleons. We know that the nucleus weighs less than the nucleons, okay, and that's just telling us what we already know. It goes on to say that Einstein's concept of mass energy equivalency equals mc squared can be used to predict the energy that binds the nucleus together by using the mass defect. And they're giving us some masses here. Notice they're giving the masses in kilograms, not atomic mass units here. We want to find the mass defect of uranium-235. Well, there's a couple things you got to recognize here. A, how to find a mass defect by subtracting these numbers or whatever. But B, how many protons and neutrons are in uranium-235. We know that uranium-235 has a mass number of 235 because they tell us that in the question. How many protons does it have? We're not told that, right? How many protons does it have? Where do you find that from? Get it from your periodic table. So we're going to say it's 92 times this, and then we're going to say, well, 235 minus 92 is 143 neutrons, so it's going to be 143 times this. What do we get when we multiply 92 times this, 143 times this, and we add those 2 together? 3.18 or 3.87 times 10 to the something? We'll pull up the calculator and do this here as a group here, okay? What do we have to do what, sorry? Okay, and that's what you got. What did you get? 3.87? Okay. Why do we have to do this? Because the uranium-235 nucleus is not going to, of course it's not going to be anywhere close to weighing the same as a single proton and a single neutron, right? The uranium-235 consists of 92 protons and 143 neutrons. So we have to add up the mass of all of those protons and all of those neutrons in order to get a mass that is greater than the mass of the nucleus itself. Okay. Well, it's not a reaction per se. It's, in a sense, it is. It's putting these protons and neutrons together to give us the nucleus. But we're not going to treat it as one of those decay equations that we saw. We're basically saying, look, the nucleus weighs less than the nucleons. Well, the nucleons isn't just a single proton and neutron. It's 92 protons and 143 neutrons. So we got to add up all of those masses. Let's say 92 times, let's use some brackets here, 92 times 1.6726 times 10 to the negative 27. We're going to add that to 143. We'll use some brackets here as well. 143 times 1.6749 times 10 to the minus 27. That's going to give us 3.93. Did I make a mistake there? You got what? Sorry? What have I done wrong there? Oh, I see what it is. I said 1.6726. Oh, that's what it is, yeah. Oh, yeah. No, I see, yeah. No, you're right. I found, yeah, no, you're absolutely right. I haven't finished the question, right? That's my problem, is I haven't finished it. I found the total mass of the nucleons. We know the total mass of the nucleons is going to be greater than the mass of the uranium nucleus. So let's now subtract from that the mass of the nucleus, 3.9021 times 10 to the negative 25. And that's going to give us 3.1799, or 3.18 times 10 to the, doesn't really matter. 3.18 is all we need to put there. All right? Now you want to find the nuclear binding energy. This one's pretty straightforward. All we're going to do is say E is equal to mc squared. Now this one depends upon, of course, question number 167. On your diploma exam, they don't do that anymore. Okay, they don't do questions where one question depends upon the previous question. They used to, but not anymore. So if you have to do a question like 168, they'll give you the mass defect. Okay? You don't need to worry about that. All right, our mass defect was 3.18 times 10 to the whatever. We're going to 10 to the minus 27. We're going to multiply that by 3 times 10 to the 8, and we're going to square that. We end up getting 2.86 times 10 to the negative 10. Is that right? Oh, once in the electron volts, yeah. Right. I've told you this a million times this year, right? When you see electron volts or non-standard units, circle it. Okay. Why did I make that mistake? Because I didn't circle it. Because I didn't follow my own advice in circling non-standard units there. Okay. So be careful with that. We want to convert that to electron volts. We're going to say 2.86 times 10 to the negative 10 joules. 1 electron volt over 1.6 times 10 to the minus 19 joules equals x electron volts over 2.86. So basically it's going to be 2.86 divided by 1.6. And we're going to get an answer of 178 blah, 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 which gives us 1.79 times 10 to the something. But of course we care about that. Good? So we had a bunch of answers in the first one that were 3.87 and some that were 30. I'm curious where that 30 came from. There was more than one person that said that. So anybody want to volunteer where you got 30 for number 167? No? All right. Are we good with these now? Okay, real quickly, let's review what we did yesterday with Rutherford's gold foil experiment, okay? We had a source of alpha particles. It's not a box of alpha particles, it's just a source of, it's a radioactive material that decays into alpha particles. Those alpha particles get released. They're aimed at this thin layer of gold foil, and then we detect where they hit this screen because this screen ends up glowing. It's a scintillation screen. It glows when these alpha particles hit it. Rutherford and his assistants made 3 main observations here. The first one being that most of these alpha particles ended up going straight through. That told Rutherford and his assistants, if most of them go straight through, then most of the atom is going to be empty space. If it wasn't empty space, then most of these alpha particles wouldn't have went straight through. They would have been deflected. They would have hit something. They would have bounced back. Okay, the fact that most of them went straight through, it's like that analogy that we did yesterday with the football field, right? Most of the people running across the football field went straight across because there was nothing in their way. Most of the football field was empty space. Now, they also noticed that a number of these, some of these, certainly less than went straight through, but certainly a measurable number of them, were deflected. So instead of going straight through, they did go through, but instead of going straight through, They ended up going up like this, or down like this, or up a little bit further. That told Rutherford and his assistants that there was something in the way. It's not all empty space. There's got to be something in the way that's causing these things to be deflected. Well, what's going to deflect? What's going to push away something that's positively charged? Something that's positively charged. It's going to be repelled by something that's positive. That thing has got to be small. It's got to be small because most of the atom is empty space. So if there's something there, it can't be very big. It's going to be small, and it's going to be positively charged. We'll call it a nucleus. A small, positively charged nucleus. The third observation that was made by Rutherford and his assistants were that a few of these alpha particles bounced back. They bounced back like this. Maybe straight back, maybe they bounced back at an angle. Few of them bounced back. What did that tell them? Well, we had these guys running across the football field yesterday in our analogy. We found that most of them went straight through. Most of the football field was empty space. A few of them were deflected. They were pushed away by something relatively small in the middle. A few of them bounced back. One or two of them bounced back. That told us that that one that bounced back, or those two that bounced back, must have hit something. They hit something that was small and positive. But that something that was small and positive must be heavy or dense. If it wasn't, let's think about what would happen. Okay? Here's my small, positive, light nucleus. Watch what happens when something hits a small, positive, light nucleus. It keeps going. We knock it out of the way, right? Watch what happens when we hit a small, positive, heavy nucleus. It bounces back, right? So the fact that this alpha particle bounced back told us that this nucleus that was already established as being small and positive, it's got to be heavy as well. Because if it was light, the alpha particle would have just knocked it out of the way and kept going. Does that make sense? Hey, good news. Here's another multiple choice question for you to work on. All right, let's take a look at it here. Students attempt to determine the nature of an object that is hidden beneath a sheet of plywood by rolling marbles under the plywood. This exercise would help students appreciate the difficulties encountered by Compton, Einstein, Rutherford, or Thomson. I mean, you can imagine, of course, in the context of doing this question here now, we just finished the Rutherford gold foil experiment. The answer is probably going to be C, and in fact it is. But why is it C? Why is it not Compton? Why is it not Einstein? In the end here, we're trying to find what's inside something without actually being able to see it. How are we doing that? We're firing something, we're throwing something at this thing and seeing what happens to them. We're throwing these marbles at it and seeing if these marbles go straight through or bounce back or get deflected or whatever. Okay, that is not exactly what Rutherford did, because he fired these tiny little alpha particles. But in the end, it's a lot more like Rutherford's gold foil experiment than it is like Thomson's cathode ray tube or Compton or Einstein with the photoelectric effect. So the answer is C. Okay. All right. Today, we're going to do our second to last topic of the year. Call it the Bohr model of the atom. We've got three models here so far, right, Jordan? The first one, the Dalton solid sphere model, which you don't really have to know much about because it's not really a physics 30 thing. Just for perspective, the Dalton solid sphere model of the atom said that the atom is just a solid sphere. It's like a billiard ball. Now, each of them are different, but there's nothing inside them that makes them different. It's just, the 8 ball is different than the 2 ball. Okay, the stripes are different than the solids, in pool, right? Inside, there's nothing different about them. Okay? Each atom is different, but in the end, each atom is just a solid billiard ball, basically. Well, then we had the Thomson model of the atom, which said that the atom consists of a sea of positive charge with a whole bunch of little negative electrons floating around inside it. That was a big step forward because that helped us to see that there are subatomic particles. There is something smaller than the atom itself. Then we took another big jump forward with the Rutherford, call it the planetary model of the atom sometimes. Planetary because it's electrons orbiting around a nucleus just like planets orbit around the sun. Here's my nucleus. Here's my electrons orbiting around that nucleus, the Rutherford model of the atom. Now we come to the Bohr model of the atom. Niels Bohr said, you know, I think this guy Rutherford had a lot of good things to say about the atom. In fact, he says, I'm paraphrasing what he said now, but Bohr said, I can live with a lot of things that Rutherford said about the atom. The fact that there was a small, dense, positively charged nucleus, yeah, I can live with that. Okay, that makes sense to me. The fact that most of the atom is empty space, yeah, I can live with that. That makes perfect sense. Okay, Rutherford's experiment shows that very well. The fact that the electrons orbit around the nucleus, sure, I can live with that. The fact that the electrons can orbit around the nucleus anywhere they want, he says, I don't think I can live with that one. The Bohr model of the atom says all of those things that the Rutherford model of the atom said, but in addition, it says those electrons that orbit around the nucleus have to be in certain places. There are what we call electron levels. Each level is characterized by a certain amount of energy. So you can have an electron here or here on this energy level or that energy level, but you can't have an electron somewhere in between. It's kind of like you're running a race out on the track, okay, 400-meter race out on the track. You've got to be in lane 1, or you've got to be in lane 2 or 3 or 4 or 5 or 6 or 7 or 8. You can't be in lane 1.5. You can't be wherever you want. You're told you're in this lane. Electrons have to be in one lane or another, one energy level or another. They can't just orbit around anywhere they want. Now, they will fill in those inner levels first. Okay, when I run around the track, I always run around the inner level first. Okay, I only do that because I know the inner level is 400 meters around, not because it's any easier to do the inner lane than it is, say, the outer lane. I just know what that distance is. But in the end, that's where I always go. I always fill in that inner level first, and that's what electrons do as well. Okay, if there's 2 spots for electrons in that first level, then you're going to have your electrons fill in those 2 spots first. Okay, if there's 8 spots in the second level, and the first level is already filled in, then you're going to have those 8 spots filled in next. I still go to Flames games, but when I used to go years ago, back in the late 90s, and nobody else really went to Flames games, I would spend $8 and get a Sport Check Zone ticket. It wasn't Sport Check Zone at that time, but the rafter seats. I would spend $8, get a rafter seat, and I would watch for about 10, 15 minutes, watch the lower deck, and see what seats remained empty for the first period. And then what would I do? I would move down. I would spend my $8, and then I would move down to the lower seats. Okay, I would fill in those lower vacant levels. Okay, if there's a spot for 10,000 people in the first deck, and there's only 9,998 in there, well, then I'm going to go down and take one of those spots. I'm going to fill in one of those vacancies. Okay? There's only a certain number of people allowed in the first deck, but we're always going to fill that first deck first. All right. The second thing that Bohr said that differentiated it from the Rutherford model of the atom comes down to something that we call stationary states. When we learned about electromagnetic radiation, we learned that accelerating charged particles will emit electromagnetic radiation. Maxwell's theory of EMR says you get an accelerating charged particle, it generates EMR. Well, as an electron orbits around the nucleus, it's accelerating, not because it's speeding up or slowing down, but because it's going in a circle. It experiences a centripetal acceleration. but it doesn't emit EMR. If it did, take a look at my keys up here as I swing them around my head for a second. If it did emit EMR, it would be losing energy. And if it lost energy, watch what would happen to the electron as it loses energy. It would spiral in towards the nucleus, right? It wouldn't stay in orbit around if it kept losing energy. That doesn't happen. Electrons don't emit EMR as they orbit around the nucleus, as they experience that centripetal acceleration, contrary to classical electromagnetic theory, which says they should. Bohr just kind of ignored that. Kind of said, well, they just don't. It's as if they're not even moving. They are moving. They're orbiting around the nucleus. But it's as if they're not moving. It's as if they're stationary. Okay, electrons don't emit EMR. As they orbit the nucleus, even though they do experience the centripetal acceleration, that AC is equal to v squared over r. They experience that, and Maxwell said, yeah, they would emit EMR as they do that, but they don't. And we know that they don't because these electrons don't spiral into the nucleus, which they would do if they gave off energy in the form of EMR. The third part, we talk about electron transitions. Electrons, if they absorb energy, and that energy would be in the form, by the way, normally of electromagnetic radiation, they will jump to a higher level. When I used to sit in the sport check zone at the Saddledome, that's a long way up. You ever sat up there? You gotta walk a long ways. A lot of stairs to get up to the sport check zone. You better make sure you've eaten your Wheaties in the morning, or your Vector cereal in the morning, or you've had your Red Bull before you go up there. You need to absorb energy in order to go to a higher level. Okay, electrons absorb energy to jump to a higher level. When these electrons give off energy, and that energy will be also in the form of electromagnetic radiation, photons, right? Visible light, ultraviolet, infrared. When they give off energy, it's because they're falling to a lower level. I'm at the very top deck of the Saddledome. I'm a mile from the ice. And I decide to stand up in the aisle. Get up out of my seat, stand up in the aisle. Joel was sitting right in front of me. As I'm walking, Joel sticks out his leg and trips me. And as I fall down those stairs, as I go to a lower level, I give off energy. I scream like a little girl. I give off energy as I'm going to a lower level. Okay? Electrons, when they absorb energy, they go to a higher level. When they give off energy, when they emit photons, they're going to a lower level. Now, all of this stuff is in addition to what Rutherford said about the atom. Okay, we're not discounting the idea of that small, dense, positively charged nucleus. We're not discounting the idea of the electrons orbiting the nucleus. We're building on that. Okay, we're refining that. That makes sense? Let me show you a picture here. This picture, or these three pictures, show three different types of spectra that we can get. The first one is what we call a continuous spectrum. We've talked about this before, right? A continuous spectrum. It's like a rainbow. If we take a hot, solid, a liquid, or a gas at high pressure, it will emit electromagnetic radiation. In fact, it will emit white light. That white light doesn't look like red, orange, yellow, green, blue, indigo, and violet. It looks like white light. It looks like the light that we're seeing right now. But if we put that white light through a diffraction grating, or we could put it, what else could we put it through? A prism. Okay, if we put it through a prism or a diffraction grating, then it will split up that white light. Okay, if we split up that white light from this high pressure source, then we're going to get a continuous spectrum. Now, if we have a hot gas under low pressure, it's also going to produce multiple colors. But these colors are going to correspond to EMR that's given off as electrons make transitions from high levels to low levels. Those are going to be discrete colors. Those are not going to produce a continuous spectrum. Okay, we're going to get discrete colors here. Each color corresponding to a particular transition. Now, when we put them together, it still looks more or less like white light. But when we put it through a prism or a diffraction grating, it splits it up, so that we end up getting this not continuous spectrum, but we get a bright line spectrum, or what we call an emission spectrum, where we've got a green line that corresponds to one transition that's taking place, going from a high level to a low level. We get a yellow line corresponding to another transition, a couple green lines corresponding to two more transitions, a blue line over here that corresponds to another transition. Each line, each color, each frequency or wavelength corresponds to a different, unique transition that's taking place from a high level to a low level within that atom. Now take a look at what we see at the bottom here. Here we see that incandescent source again, that light bulb, that would, in the absence of this cold gas, produce exactly what we see in diagram 1, a continuous spectrum. It's exactly the same picture right now. But as soon as we introduce this cold gas, what happens? Well, the cold gas starts absorbing photons. It starts absorbing EMR. So some of this white light that came from this high pressure incandescent source, some of that white light gets taken away. We get the continuous spectrum minus the red color that was taken away. We get the continuous spectrum minus the yellow color that was taken away by this cold gas. The two greens that were taken away by the cold gas. The blue that was taken away by the cold gas. So because it's a cold gas, it has the ability to absorb energy, to absorb EMR, to absorb light. As it does that, electrons make a transition from a low level to a high level. Instead of seeing the continuous spectrum that we would see because of this source of light here, we see the continuous spectrum minus the frequencies that were taken away. Carson, does that make sense? Is that good, guys? So we got three types here. This continuous spectrum that's produced by a high pressure solid, liquid, or gas. We've got this line emission spectrum, or a bright line spectrum, sometimes we call it, that's produced by a hot gas under low pressure. Okay, very discrete types of EMR as opposed to all of them. And we have this incandescent source, this solid, liquid, or gas under high pressure again, that's producing a continuous spectrum, but losing some of that spectrum due to the cold gas absorbing certain photons and causing them to jump to higher levels. Now, what's kind of neat about this is that every different element, almost finished here, every different element has its own unique spectrum. Every different element looks a little bit different. Real quickly, let's take a look at this, and then we're done for the day here, okay? Hydrogen gas looks like this. Helium gas looks like this. Sodium gas looks like this. We have an unknown gas mixture here. Tell me what's present in that unknown gas mixture. What do you see in there? Do you see hydrogen? Do you see helium? Do you see sodium? Do you see some sort of combination? Well, I'll tell you what, we know sodium's not there. Tell me how you know sodium's not there in that, we know that sodium's not there in that unknown gas. Some of the lines that are produced in this sodium spectrum aren't there in the unknown gas. So we know sodium isn't present. These ones are. Oh, sorry, no, sorry. Going the other way around here. Helium is not present, right? Helium isn't present because we see this one here that's in helium. It's not in the unknown gas. We see this one, it's not in the unknown gas. So helium's not there. What about hydrogen and sodium? Well, all of the lines from helium are there. All of the lines from sodium are there. So what do we know about this unknown gas mixture? It's helium and sodium. You look at the stars. You discover something in the sky that nobody's ever seen before. You look at it through a prism or a diffraction grating, basically a spectrometer. You observe the spectra and you say, wait a second. I've just determined the composition of this star. I've just determined what's in this star by comparing the spectrum of that star, this unknown gas mixture, with other known spectra. All right, that's it for today, guys. Have a good night. Sorry, that should be hydrogen and sodium, not helium and sodium. Hydrogen and sodium. Okay? Now that's it for today.